This is good. It's almost like broadcasting a TV show. There you go. Going live. Good.
Okay. Welcome to the last day of this workshop. So with respect to the program that is online, we changed slightly the schedule today. So we will have this talk, then a coffee break at 10:30 after the talk. Then the second talk will not be at 10:30, but at 11, so from 11 to 12. Then we will have some time for discussion with the speakers, and then we'll have the lunch before the workshop is over. Okay, so the first speaker of today, it's a great pleasure to have Nayshesh Afshordi, and he will talk about simulating Hawking radiation. Please. Okay.
Thank you very much, Paolo, and thank you guys. Congratulations, you made it. You have managed to stay to the end of the conference. Not everybody did, but you were the brave ones that managed to make it to the end. So great, and hello everyone on Zoom. So I'm going to tell you about a topic that in fact was started by no other than our chair, Paolo. Basically we took it from him and then took it places that I think he didn't want to take it, but we did anyway. So I'm going to tell you about stimulating Hawking radiation, and don't hesitate to interrupt me at any point, and how we got to it, basically the story of it. So let's see whether I can actually, okay, good. So the story actually starts a while ago, and it's within a span of 7 months in 2 papers that probably you recognize at least one of them, but probably both of them. They are both by Einstein within a span of 7 months. This is in 1916, July, and then this is in 1915 in November. So one is on quantum radiation, stimulated, what we now call a stimulated radiation, and spontaneous radiation and absorption, and how in quantum mechanics they can balance and give you thermal equilibrium. And another, of course, what is more familiar, we talked about in this course of this week, is the celebrated Einstein's equations in theory of relativity. And the story of this talk is how these 2 papers of Einstein face off against each other. Okay. And these are in the middle of the First World War, by the way, so it's an interesting time to think about foundational problems, which I guess says there's really no bad time to think about foundational problems. And this is, in particular, this equation, I want to pay, you recognize all you from kindergarten, this is how in thermal equilibrium, these various processes, absorption, spontaneous emission, and stimulated emission are in equilibrium. So that's this equilibrium that you recognize. Okay, so with that introduction, this is the outline of the talk. I'm going to talk about black holes in gravity, then black holes in quantum mechanics, and then how these 2 can come together. Okay, so this is familiar by now simulations of binary neutron star mergers. It was a great achievement that we managed to make these kind of simulations, and let me go back, run this again, yeah. But it was even greater to see this happen in real world and form a black hole in the middle. So these simulations were from 2015, or I think even earlier, I don't quite remember, by Luciano Rosallo's group. And there is this same process being observed in the sky by LIGO collaboration very famously. And in fact, it's been detected both in various electromagnetic wavelengths as well. But what we know is at the end of this, at least most people agree, we form a black hole, and the relativity predicts that you form a singularity, which is shrouded by an event horizon. And in classical relativity, these event horizons, as we know, as the title of this workshop suggests, are not very special places. But as we've heard, and we're gonna discover more about this, the special things may happen in the horizon in quantum mechanics. So, and of course, you all know about this, but I just want to put this here because we're going to come back to all of these during this talk. So Hawking and collaborators discovered this series of black hole thermodynamical properties from classical general relativity plus some elements of quantum mechanics, or quantum field theory in curvature space-time, I should say, that there is a temperature to a horizon, which goes as surface gravity over 2 pi. There's an entropy that goes as area of the horizon divided by 4g. And then there are laws of thermodynamics that holds for this temperature and entropy the same way it holds for any other quantum mechanical system that we know. And the entropy seems to always increase. That's the second law. Okay. The real question, and it's a question that Josef's talk, in fact, touched upon very, very much so from a couple of days ago, is which states this entropy is counting. So from a string theory point of view, these would be fuzzballs. At least the camp who's here says fuzzball, and the other camp, I guess we don't care about them since they're not here. But in other theories of gravity or quantum gravity, these microstates could be other things. And it's really up to any proposal for quantum gravity to say basically what this entropy counts, or what's responsible for entropy of black holes. But classical relativity tells us that there is an entropy, but it doesn't tell us what it's counting. Okay, so that's we're gonna, and then of course the other thing we learn in textbooks these days is black holes emit Hawking radiation, and they explode, and these are basically kind of things that are well accepted in the community. Okay, so that's a starting point, and these are again things that we all learn in kindergarten one way or another, maybe primary school, but the question is that are these, do they make sense? Are they consistent with each other? And here is where Einstein's second paper comes in from that 7-month period, which involves quantum radiation. So it turns out that there is something wrong with the story that I just told you, or the story that you're told in primary school. And there are various ways of putting what's wrong with it. The most famous one is known as the information paradox, which I'm going to get back to, but most recently it was presented by Samir Mathur and Amps, who you probably recognize. I'm going to tell you who Amps is in a minute. Basically, they argue that local physics plus a smooth horizon cannot be consistent with unitarity of black hole evaporation. But in some sense, more interestingly, as Josef referred to a couple of days ago, what's special about forming horizon is all the stuff that you thought were exponentially suppressed suddenly come out of the shadows, because this exponential suppressing of quantum tunneling, which you can usually ignore on larger scales, suddenly is canceled with the exponential of entropy as you form a horizon-sized objects. And everything basically that you learn and love about classical or semi-classical relativity goes out of the window if you believe that this cancellation happens. And as he referred to, and in fact, Daniel, did you do this calculation first that's showing that these two cancel? I'm trying to remember. Mm-hmm. Right, so you did a very concrete.
This is the generic argument saying.
Right. But Daniel did a very concrete calculation, and then Samir, Mathur, and Cross did also more general arguments that there is this cancellation. So that suggests that basically the semi-classical picture goes out of the window as soon as you form horizons, or very close to when you form the horizon. So in fact, how I got into this, which I'm not going to talk about, is trying to connect to understand dark energy, because cosmology is my background. And in fact, we showed with my former students in papers that were published a long time ago, and another is still in progress, that you could, in fact, even explain the scale of dark energy if you couple dark energy to the horizons at the expense of basically giving black holes a quantum hair. Or in other words, in fact, in this scenario, there is no horizon, but dark energy is a type of quantum hair for black holes. So, but these are like different lines of a story, but what they all suggest is there might be something not quite right with the classical picture of horizons. Now, one of them is, the most famous one is known as firewall paradox, which is in fact first suggested by Samir Mathur, but it was more, I guess, evangelized by Almeri, Merrill, Fulchinsky, and Solly. And that was the statement that these four kind of tenets of black holes that we learned early on cannot be all consistent with each other. Unitarity, equivalence principle at the horizon, quantum field theory or locality outside the horizon, and then area law, basically, that we talked about. So these cannot be all consistent with each other. And there have been lots said about that, but essentially people have to, everybody, I mean, decides to give up on one of these. Okay, so what we are going to do is to argue that the most conservative, kind of follow this lead, that most conservative approach is to get rid of the horizon one way or another. And although there is a fine distinction between the firewall and fuzzball, but that's not going to be very, and I know people, I know Samir is very emphatic about it, but I'm not going to kind of dwell too much on that distinction. The main thing is that classical physics breaks down at the horizon, and I want to take that point of view and see how that can be tested in observations. Okay, so actually before I get there, I just wanted to say that there are different ways of going about this, asking what happens at the horizon, and something that we did recently with Aaron Held and Johanna Bersava. Aaron is a postdoc at Princeton. Johanna is a student at Perimeter. That we try to answer this question in the context of a different theory of quantum gravity that we don't often hear about. It's known as asymptotic safety, which suggests that you could UV complete gravity through basically the normalization group, and there is a non-trivial UV fixed point. So there is a community that's mostly active in Europe who work on it. And in fact, Aaron came out of that community. And we kind of try to use the principles of asymptotic safety plus an assumption that the RG scale is given by temperature, because black hole is a thermodynamic system. And then RG improved the black hole solution in the context of asymptotic safety. Basically take Einstein-Hilbert action, but say that lambda and G are not constants anymore, are now RG improved. They could depend on the UV scale. And lo and behold, what we found is that if you look at the black hole solutions in this theory, then they look like Schwarzschild far away, but then the horizon disappears, and then what you get is a scale invariant core, basically. So their metric goes as some irrational power law at the center. And I mean, the bigger the black hole is, the smaller the metric is in the middle, but it never actually crosses zero, so you don't actually have a horizon. Sorry?
Are you plotting?
Oh yeah, so this is the, oh yeah, somehow something happened to my axis. So this is logarithm of radius, and this is log of G00. So, oh yeah, actually here, there it is. This is log of G00 is this axis. So in Schwarzschild, this would be just go to minus infinity because G00 crosses 0. But then here, in fact, it goes down and then it becomes a power law. So you get a very big redshift to get out, but it's never infinite redshift. Okay. So this is one way of UV completing. Now, I mean, this is the toy model for asymptotic safety. One can argue all asymptotic safety calculations are toy models. One can argue that all models with quantum black holes are toy models. But this is an example from something that is not a string theory. of course, the thing that we did hear about this week is our fuzzballs in a string theory. And there the idea is that you replace this classical picture with a quantum picture of a stringy fuzz. It could be classical geometries in some basis, or maybe something much more non-classical, depending on your point of view. And what happens is Hawking radiation is basically a spontaneous emission of excited states of these fuzzballs to a slightly less excited state of these fuzzballs. And in fact, Samir and company have shown that you can get ergo region instabilities in these fuzzball geometries that lead to Hawking radiation. Yes?
J-Mart-like solution, J-Mart, Jajala, Masen.
I don't know, actually.
Okay.
I'm not. Yeah. Okay, good. Let's see. Okay, so now on to the story of what happens if you get rid of the horizons. So this is something, as I mentioned, Paulo, Cardoso, and Franzin first pointed out in a couple of papers in 2016, right after LIGO came out. And just as soon as their first paper came out, we got excited about it. In fact, I never worked on gravitational waves, but as soon as I saw their paper, I said, okay, it's time to jump ship. Cosmology is finished. Everybody needs to work on black holes now. And basically what we realized that is now that we understand the cosmology very well, we need to do the same thing we did with cosmology with black holes, just try to look deeper and deeper. Well, instead of looking farther and farther into Big Bang, look deeper and deeper into the black holes. So what is the tool? So what Paulo and company realized was that if you put something near the horizon, if the horizon for one of these quantum magic reasons that I described disappears, then it doesn't have to be a one-way classical surface or classical event horizon or classical null surface. It could actually reflect the stuff, and if it does, then you expect to see reflections or echoes in gravitational waves. So this is an example of what you expect to see for the first event that LIGO saw. So this is the main GR signal that you expect to see. And this is not modified a lot because this fuzzball lies very, very deep in gravitational potential, and it takes time to actually reach it. So early times, you don't actually know that horizon is not there. But then eventually you find out when the signal reaches this membrane or fuzzball, and then they can at least get partially reflected, and then you see echoes. And these echoes, in fact, you could predict rather precisely, even though we don't really know what these fuzzballs are, you could predict rather precisely when you see them or you hear them, if you assume that they come from Planck structure. And I'm going to actually give you some arguments that you can make this argument, make this in fact even more precise than that, given the black hole entropy. So for the first event that LIGO saw, it was 0.3 seconds and has a very predictable dependence on mass, on a spin, and also there's a logarithmic dependence on mass and Planck, which this log gets big, but it never gets very big. It's of order of 100, which is very convenient, which is because it parametrically separates echoes from the main GR part. And of course, I mean, there is no astrophysics happening here. It's in a sense, there is no gas. It's just, unlike most other problems that we're dealing with astrophysics, separating fundamental physics from dust is a problem, but there is no dust around black holes, as far as I know. So this is a clean signal if it's there. Okay. So, and this is work we first did with Jahid Abadi and Hannah Daikar. I'm going to come back to what we found, but this is basically the signal. So before we get to the observations, I'm going to tell you a little bit about the work that has been done since about what we expect to see, because this was all uncharted territory. When you something, if there is something near the horizon, something should come out. But then, as I told you, we had never worked on black holes or gravitational waves. So there was a process to at least start the guesswork as to what that something might be near the horizon. Now, of course, Daniel and others have thought about fuzzballs in other contexts for a long time. But there was a learning process. And then what that something that comes out might be, that was another learning process. And that's still a process, but I'm going to tell you what we learned. And in fact, that's the title of the talk, the Stimulated Hawking Radiation. So what my student and postdoc, Qingwen Wang and Naritaka Oshita discovered together, in fact, Naritaka kind of discovered this out of nowhere, was there were a variety of ways that you try to model this fuzz near the horizon, and they all give you the same effect. Now, I mean, there is way, if you don't put anything near the horizon, you don't get anything. But if you put something, and it seems that doesn't really matter what that something is, the various ways, if there is some quantum element in it, then you get a reflectivity. And the reflectivity is a very familiar formula. It's Boltzmann. So what it suggests is at high frequencies, things that are small, just see a classical horizon and then shoot through it. But things that are big, the long wave packets comparable to the Hawking wavelength, they actually fill the horizon, and then they just don't go through. They can get partial reflection or significant reflection. And interestingly, this is something that, go ahead, Daniel.
So just so I understand correctly, this is sort of the exact opposite picture of like with a firewall, where the higher energy guys will see the firewall and the low energy guys just kind of have, you know, if you're low enough energy, you just see like semi-classical evolution. You don't see anything going on, and then high enough energy, you hit the firewall or whatever.
I mean, to be honest, I don't really know what is a picture of a firewall.
Yeah, sure. But you're saying it's really this opposite energy kind of thing. Yeah. The low energy guys are the ones who are affected.
Exactly. Yeah. The high energy ones, they just pass through. They don't see anything, basically.
So in terms of like what's the name? Correspondence principle. Like this is sort of violating that, right? Because you're saying that if you fall in as a semi-classical observer, you will see something because you're low energy then.
Well, okay. So that this is the thing. There is a question of energy versus frequency. Okay. Because you could have high occupational states, right? And this is a statement about frequency, right? But then when you want to take it to energy, that becomes more subtle, and I don't have a good answer to that, to be honest. Yeah. So this is, yeah. Go ahead.
Why do you expect this at the horizon and not at the photosphere?
This is near the horizon. Although actually, exactly where this is happening, I'm going to come back to that. This doesn't tell you where it's happening. It just tells you how much it's happening. It tells you there's a reflectivity. And in fact, Samir Mathur had a name for this, even though he didn't have a formula. He called it fuzzball complementarity. So he said that basically high energy things, the high frequency things, they just pass through, and low frequency or low energy things can actually see the horizon. And this quantifies that. Yeah.
Yes, so my question is, why do you expect at the horizon? Because, for example, for fastball, you don't have the horizon, but you have a photosphere.
So I'm going to come back to that. So this doesn't tell you where it is, but there's a different argument that tells you where it is. Good.
Okay. Because if it's happening at the light rings, I would not expect the temperature of the horizon, but something is.
Yeah, absolutely. This is not happening at the light ring, and we're going to come back to where it's happening.
There are supersymmetric and BPS microstates that still have a reflection, a non-trivial reflection, right, and the temperature is 0. So this formula may be valid for generic.
Yeah, this is for finite temperature. I think 0 temperature, it's a different story, which this doesn't cover. I don't have a good story for that.
This is the reflectivity of the fastball, not of the photosphere. And
you mean for 0 temperature? Yeah, I don't know. I mean, I think the arguments we have, these are thermodynamic arguments, and at 0 temperatures, they don't work. So I don't have a good argument. I mean, I think there should be, in fact, the next talk by next speaker is going to talk about what happens for this 0 temperature. And I mean, you generically expect echoes because there is no horizon in it like this. But the kind of arguments that we use here only for finite temperature. Yes.
So I have a basic question, since I'm not an expert of black holes. So I previously thought echoes were related to quasi-normal modes, so to space-time damped oscillations. But now I read you say they are stimulating Hawking radiation. They are a quantum phenomenon, not so they have this difference.
So there's
okay.
Yeah, so it turns out that a stimulated Hawking radiation could be, or stimulated emission could be a classical phenomenon, and it's an interesting because of essentially particle wave duality. So you could think about emission of basically large amplitude electromagnetic waves as a stimulated emission, because basically there is a large occupation number. So it is a quantum phenomenon, but there is a classical limit to it. And here you are in that classical limit. So there is no contradiction there.
Okay, thanks.
Good. Very good question. So I don't want to take you through all of these arguments because they are a little bit involved. I mean, they're actually very simple arguments, but there are different ones, and it just takes time to go through them. But I want to outline where they come from. So we have a bunch of different arguments that they all give you the same thing, and they all have some quantum elements in it. And what they give you is that echoes lead to a stimulating Hawking radiation. And most of it happens at horizon frequency. Because this formula, it looks like it's the biggest at low frequencies, but these horizons are rotating. Then, in fact, this is maximum not at zero frequency to outside observers, but at the angular momentum number m times horizon frequency. So usually for gravitational waves, m is equal to 2. So this is not, in fact, peaked at 0, but at some finite frequency, as we're going to see. Okay, so where do they come from? So the first one is, in fact, from the fluctuation dissipation theorem. What Naritaka noticed is that if you add dissipative effects to the dispersion relation, and this is something you expect, because if you have microstates sitting near the horizon, things that fall into the horizon should dissipate at some point, because they're going to blend with the microstates. And we just added some very simplistic dissipative effect like this with some cutoff. And it turns out if you just solve, independent about this cutoff, if you solve the wave equation with dissipation as you approach the horizon, you get deflection. And this is a movie, basically, that shows how this happens. It's not exactly for this, but it just demonstrates the phenomenon that if you turn on dissipation very abruptly, that's just the property of waves. That leads to reflection. So, which is kind of counterintuitive if you think about it, that dissipation leads to reflection, but in fact, that just comes from basic optics that you learn in undergrad. That whenever there's a sharp transition, there is reflection, and this, and basically for long wavelength fluctuations, if they hit the horizon, they see a sharp transition. So that's where we got it first, from just solving wave equation. But then we got the same thing from a very simple argument, essentially what Einstein did. So if you imagine the spontaneous emission is Hawking radiation, as we discussed in, for example, in fuzzball, or essentially any theory of quantum black holes that does have Hawking radiation. Then anytime there is a spontaneous emission, there could be a stimulated emission. You just need to stimulate it. And whenever things are falling to the black hole, or into this quantum structure at the same frequency that radiation is happening, which is Hawking temperature roughly, then you could stimulate it. And that's basically what we're imagining, that if you have incident radiation, and that could stimulate emission, if your incident radiation is at the same temperature as the black hole, then these processes equilibrate. This is basically a spontaneous plus a stimulated emission, as this happens at the same rate as happens at the same rate as absorption here. But then if you have classical incoming gravitational wave, then a stimulated emission becomes much bigger than a spontaneous emission, right? Because it's stimulated. And basically what you find is that these don't cancel each other. The ratio of a stimulated emission to absorption becomes this Boltzmann factor. And this is just, again, classical. Just following what Einstein had in his paper, you get this Boltzmann factor. So yeah, it's kind of interesting that you get purely classical calculation by solving a wave equation in Einstein plus dissipation, but then this is purely quantum calculation based on Einstein's other paper, and they give you the same result. Right. And then there is a completely different out of nowhere result, which is if you just take black hole space-time and split it in half, and this is something that a lot of people who are working on black hole information, in quantum information of black holes, for example, this paper is from Hayden and Pennington, and they argue that basically there are a lot of expectations you have from quantum communication that if they are satisfied, then a structure at the horizon, well, it should be some non-trivial structure at the horizon. And then one of the possibilities is this Hartmann-Maldacena state, where you basically split the eternal black hole in half and then identify the two sides. So this is like a mirror that sits here.
Nature is not CP invariant.
It's not CP
invariant.
That's right.
So this argument is in a pure gravity in which no matter like standard model matter is present. Fluctuations of standard model matter would violate.
No, absolutely. This is not. I'm not saying this is a fundamental property of nature. I'm saying that these states exist that seems to have good properties that basically don't have the pathologies that regular black holes have. And these states have this symmetry basically. Basically what it is just they have reflection. This side, where was the others, like the other half of the eternal black hole doesn't exist. So this is a semi-classical picture. This is not fundamental. And it cannot even be something that lasts forever, but it's something that has the right properties that this could last for long enough period of time, right? Now, what it is interestingly, if you just take this as space-time and then look at what happens, because there is a mirror here, for every ingoing mode, there would be an outgoing mode because there is a mirror. You notice that the mirror is inside the horizon, right? This is the horizon, but nonetheless, if you think everything is analytic, for every ingoing mode, there's an outgoing mode. And then if you go to the basically black hole coordinates, which are outside the horizon, you get exactly the same reflectivity. So this is, again, completely different line of argument based on this assumed symmetry, and it gives you exact same result. So we thought there must be something to this, because no matter how you go at these properties of quantum black holes, you get at the same thing, which is this Boltzmann reflectivity. And in fact, you don't even need quantum gravity. We did a calculation in QED with a former student of mine, who's now actually a PhD student with Thomas Hartmann at Cornell. We just did QED in curved space-time. So what we did was we looked at what happens when photons approach horizons. And what we know happens is that temperature goes up as you get very close to the horizon. So you get a plasma of Hawking electron positrons outside the horizon. And what we all learn in a school, if you take a plasma physics course, is that when there's a plasma, photons become massive. So, so if you have low frequency photons, like for example, radio waves we have in Earth, when they hit the ionosphere, they get reflected because there's a plasma density and low frequency things cannot propagate through this. So that's exactly the same thing, it turns out. So low frequency photons, when they get close to the horizon, they see this plasma, and there's a plasma frequency that's comparable to the Hawking temperature, and then they get reflected. The high frequency photons pass through, but the low frequency photons get reflected. And you could do the same calculation in basically in Schwarzschild coordinates, where you do see this plasma, or you could do it in Minkowski, where when you have this one loop. I actually got this, sorry, I think, yeah. So this is basically one loop corrections to the photon propagator in QED. And you have it in Minkowski, but you could project it into real coordinates. And you get the same results, is because it's really the same thing. So you get reflectivity, which is again, it has a Boltzmann suppression. But here, since we're doing QED, we're not doing gravity. In fact, there's an alpha QED squared here because it's really propagation. This is a scattering of these electron positrons near the horizon. So if there was no interaction with electron positrons, there would be zero reflection. But it's interesting because it tells you that these are loop effects that are responsible for this. It's not free. I mean, people usually when do QFT in curve of spacetime, they're thinking about free fields. But these are not free fields, these are interacting fields. And if you replace alpha QED with alpha gravity, when alpha for gravity depends on energy, turns out because gravity is non-normalizable, you recover the same formula, you have some order of 1 times the Boltzmann factor. So, so this is the story. So this is why we're convinced that there is something to this formula which you could think about it as a stimulating Hawking radiation, as I argued for you. And you could derive it from, it's not some property of some assumed thing about, I don't know, fuzzball necessarily, or firewalls, or even quantum gravity. It's something that inherent to the geometry plus some quantum element. And it could be different ways of getting that quantum element. But if you put it, you always get the same thing. So that's kind of the story. Any questions? Okay.
Physically, I can understand that the plasma would create, made the photon massive, but yeah. How can you make the graviton massive? So the effect
yeah.
is not clear to me.
No, I mean
the formula, the analogy is.
This is an analogy. I mean, at some level, we don't have a theory of quantum gravity, right? So whatever we do is going to be somewhat of a toy model. So we have to kind of take something seriously, but not all of it. And I mean, here you could say this is good because the full theory, quantum electrodynamics, is a renormalizable quantum theory. So we understand everything in it. But then, yes, I mean, going from there to gravity is kind of a leap of faith. Dimensionally, it works, and that's what I'm saying. But that is not beyond. We could do it in string theory. I agree, but I hope maybe you could do it because I cannot do it. Yeah. Okay. Yes.
Could you interpret this is like a time scale, no? It's in front of omega, this constant. Could you interpret this as the time that take a photon to come from the?
Oh, how long it takes? Good. Okay. Perfect. That's the next topic. Perfect timing. Okay, so now I told you what happens. Then the question is, when does it happen? And interestingly, the answer comes from somewhere that, I guess from string theory, or at least some people, one of the founders of a string theory. The first time that we heard this, and I don't quite understand why they were thinking about this, maybe someone else knows, but this in 2008, as Sekina and Susskind suggested, black holes are fast scramblers. And basically, the fastest that you could scramble quantum information has something to do with temperature. It's basically beta, which is 1 over temperature, times log of the number of degrees of freedom. Now, this n, it's a little bit context dependent, but I think in most contexts, it's the same as entropy, although in holography, this is, in fact, you could also relate it to the dimension of the gauge group. But yeah, so this is where it started. So I mean, most systems can thermalize, but it takes a long time for them to thermalize. Sekina and Susskind argue that black holes, because they have very strong interactions, they could thermalize very fast, but not faster than logarithmic. And this actually, they got this from a kind of a black hole-like calculation, and we're going to see where that comes from, or well, kind of similar to the echo calculation that Paolo and company had, to be honest. So what my student Krishan Saraswat, who is here somewhere, I think, yes, so you can see him, that's Krishan. So he actually went through various ways of calculating this scrambling time from holography. Basically, there are these various ways of talking about what the scrambling is in Ryo Takanagi and these quantum extremal surfaces. There are a bunch of ways of arguing when things are scrambled, when they fall into the black hole. And then he compared them to the echo times, basically the time that Paolo and company calculated. And he did it in various contexts for ADS, big black holes, small black holes, charged black holes. And it turns out invariably in all of them, if you define things precisely, and it's somewhere, yeah. So the scrambling time turned out to be the same as the echo time, which is this log of radius of the horizon divided by temperature, basically. So that's what he was finding, which is the same formula, essentially the same formula that Sekino and Susskind had, although depending on like what black hole you have, I mean, what n is and what beta is would be different. So what we find was this log of radius over temperature essentially was the most general formula that works within all of these contexts. So it's interesting that, I mean, people were talking about these different groups of people doing very different things, and they came up at the same time. Almost exactly, even there's no factor of 2 difference to be in 4 dimensions. And we kind of dug a bit, Christian dug a bit deeper. So now this is not a first principle calculation, but what it is now, at least in holographic context, people are thinking about black holes as random matrices. And these SYK models are random theories, basically a bunch of spins that randomly interact with each other. And then what Christian showed, that is if you kind of look at properties of random matrices, but you generalize the spacing of statistics in a particular way, then you get echoes in thermalization behavior. So this thing, you don't have to care too much about it, but it's something that quantifies thermalization. And late time behavior tells you, basically, this is approach to thermality. And usually, it's kind of a smooth approach. It's called the ramp. But it turns out that if you kind of play a little bit with the spacing of statistics, basically make eigenvalues repel each other more than usual, they're called Q ensembles, or sorry, beta ensembles, then you get these oscillations. And interestingly, this is also related to the talk we heard yesterday, because we could also show, and these are really related to each other, another way of getting these oscillations are additional symmetries. So if you have a completely random matrix, then you don't get distribution of eigenvalues, basically you don't get echoes. But then if you add additional symmetries, then your eigenvalues get into, basically go into degenerate subsectors like this. And then this does give you echoes. But to some extent, it's kind of, it's what you have in ordinary quantum mechanics, so it's not very surprising, but it suggests that if there are hidden symmetries of a random matrix, then it generally gives you echoes. So, I mean, it's just something that to think about, at least in a holographic context, to see where this may come from. Okay, so how much time do you think I have? 15 minutes? Okay. So I'm going to try to wrap up. Well, I mean, there is an exciting, controversial part, but we'll see where. Okay, so I'm going to, so there's another way we got this from CARE CFD. So if someone is interested, we can talk about that. But that's also relies on hidden symmetries, a particular version of them. So we're going to hear about echoes from fuzzballs, from Taishi. So that's quite generic. Indeed, you could get it from various scenarios. I'm going the wrong way. Sorry, there's a delay here, and I don't know. Oh, yeah. Oh, okay, I see. I think I had 2 versions of the same slide. Okay, so let me tell you, and I hope this is an argument related to your question, where they are, when you expect to hear them. So there is something very contradictory, and I think this is the most in-your-face argument that I've seen, that horizons are inconsistent with quantum mechanics. So we all believe Hawking, at least in terms of his Hawking effect or radiation, black holes radiate. So if you have a black hole and then look at this tortoise coordinates versus angular momentum, this is the angular momentum barrier of a black hole. And the horizon is this side, and then this is like photon ring, and here goes to infinity. If black hole keeps radiating, you fill this part inside the angular momentum barrier with Hawking radiation. But this is an infinite length, like in tortoise coordinates. So because it takes infinite time as far as observable infinity are concerned to actually reach the horizon. So this is infinite. So you have this infinite well, and should remember, this is in proper coordinate, proper radius, this is not infinite, but in tortoise coordinate, which is the appropriate coordinates for this calculation, this is infinite. So you have this infinite well full of Hawking radiation, which tells you that black holes have infinite entropy. Or there is infinite entropy in Hawking radiation. That doesn't make sense, right? So saying that there are horizons is the same thing as saying that black holes have infinite entropy. At least Hawking radiation that surrounds black holes has infinite entropy. If you think that doesn't make sense, if you think black holes actually have a finite entropy, which is what you expect from quantum mechanical systems have finite dimensional Hilbert space, then you cannot take this picture seriously. And in fact, the picture you should take seriously, it's very slow, is one where this Hawking radiation is cut off somewhere with some quantum fuzz. And then if you calculate the entropy of the stuff that are here, then you find that there's this will be a finite length, and there's a relationship between this distance, which is half of the echo time. Basically, if you get here and come back, that's the time of echo. That's related to entropy by this formula, which is the same formula that I was saying.
Sorry, Nayesh.
Yes.
So 2 questions. Can't I just use the same argument like doing a reflection and looking at infinity, and then will tell me that?
Yeah, but I think that's part we know, that when we talk about the entropy of the black hole, then, I mean, of course, if you have an infinite universe filled with Hawking radiation, there's infinite entropy, but that part we don't call it entropy of the black hole. That's entropy of radiation. So, but this part, this is the thing that most of it is near the horizon. So it makes sense to say call this as part of the black hole, but then the stuff that's out there, I mean, there's a clear separation of what that's not the black hole. That's something outside. Right?
Another question, sorry. So isn't there sort of cutoff due to the fact that in some time all the mass, so, I mean, there is a total entropy of the black hole that it will eventually evaporate? So it's not really infinite in this sense.
Well, I guess this is saying in thermal equilibrium. If you have a system in, yeah, I mean, I guess you're right. So if it says isolated system, you say it's never in thermal equilibrium because it's this. But if you imagine you have a system in thermal equilibrium with a Hawking bath, then it's just sitting there. And I'm saying that basically the entropy of the stuff around the black hole is infinite unless you put a cutoff. Yes, there is a stuff out here, but that's separate really here. Yeah, go ahead.
The echo time, you don't need the horizon. You can compute the echo time also for a fastball or for any compact geometry. Therefore, if you take this as the definition for this reflection, the horizon is not important. Also, the Hawking temperature.
No, very good. I think what's powerful about this is that this is for a generic microestate. Because, I mean, fuzzball, you could do calculation for a given. You can pick a geometry and do a calculation, but how do you know that's a typical geometry? These are kind of a special geometry that's very hard to come by. You have to do all sorts of tricks to get them, and there are many more of them where there should be exponential of entropy of them. But this is a semi-classical argument, but it's based on the fact that basically generic entropy counts the total number of states. So I mean, it's a simplistic argument, but it's something that applies to generic states, not necessarily, not a specific states. Does that make sense? Yeah.
I have a minor comment about this symmetry between infinity and the horizon. This is true for exactly true for extremal black holes. There is this couch torrent symmetry, and but they have zero temperature, so kind of.
Right.
I guess I don't understand why your argument. So your argument is like, okay, tortoise coordinate is infinite, so you fill it up. But of course, this is just a coordinate statement. And so I'm a little confused why this is I mean, tortoise coordinate is like a coordinate from infinity, right? And why is this different than the standard picture of, stuff falls into the black hole and it appears that if it takes a long, infinite amount of time.
That's a classical argument, right? So,
yeah, exactly. What's the difference with just saying?
I want to fill it with quantum radiation.
Sure.
And I say, okay, so what is the entropy of that radiation?
But it seems like cheating to me that you're picking a special coordinate in which
No, you could do it in a different coordinate. It's just simpler to do it in this coordinate. I mean, what happens if you do it in, say, a standard coordinates, then everything gets infinitely blue shifted. And then you do the same calculation, it's just harder calculation. Yeah, so you get the same result. The result is coordinate invariant. It's just simpler to see it here because you have plane waves here. In the standard coordinates, you get infinite blue shift, so you think, so it just look a little bit more weird. But it's the same calculation. And it's not actually even surprising. I mean, this is just a statement that entanglement entropy is divergent, right? I think it's just a simpler way of saying the same thing. But I mean, I don't even think it's a new argument. But it kind of relates the echoes to entropy in a very clear way. And in fact, there is no free parameter here. Okay? Good. So in the last, I think, 5 minutes or so, well, let's see. So, okay, so this is the part. I guess if you say this is the Hill Abonidion, that echoes to LIGO are Higgs to LHC. Of course, LHC didn't have to see Higgs, but
by the way, Nayesh, we start a bit later, so you have 10 minutes.
Okay, thank you. So LHC didn't have to see Higgs, but we have all good arguments from quantum mechanics and symmetries and unitarity that there must be something there, and there was something. And I think there's same arguments exist for presence of echoes. If you take quantum mechanics and various things like holographic principle, which comes from symmetries of gravity, seriously. Now, when we're going to detect, I mean, the same with Higgs, it was a 50-year journey. With echoes, we'll see how long it takes to get there. Okay, so, and as to basically where we are in detecting echoes, those of you who have been following this story, it's a long and complicated one. Those of you who haven't followed this story, I can give you a taste. So it all started from the paper I mentioned earlier. We looked for some toy model of things that are repeating with Jahed and Hannah Daikar, who's, coming, So it basically there's something called signal to noise ratio squared, signal to noise ratio. In fact, Daniel talked about it for Lisa. For LIGO, here the signal to noise ratio of echoes. And basically what you see is noise here. We combine this first, this is like all the story now. But we found something very expected from the time of the Planckian echoes. And we quantified it as p-value of 1%, which is interesting, but not a detection. So different people had different takes on it. Yes, go ahead. Sorry, let me just go back.
Yeah. So what are you doing there exactly? So that's T echo minus T merger by T echo, okay?
Yeah, okay. I can describe it a bit better. So we had some model for echoes, and it's just some parameterized toy model at the time because we didn't really know any better. This, like I said, this is old result. We have much better results now. So T echo minus T merger divided by delta T echo. So the idea is that things appear after some time and then keep repeating. Right. So this should be, if there are real echoes, there should be a signal at 1.
But are you marginalizing? So there will be an amplitude parameter, another
so this is basically, so a bunch of parameters that we're marginalizing over. That's right. So delta T echo is in some range. So each of these have some prior range based on theory, or whatever the theory was back then. And then we find here, this is the maximum likelihood approach. So we look what is the maximum SNR that you get for this combination of events at the time.
And so the p-value is computed from the maximum likelihood.
Right, so the p-value is that, if you do this with random, in which this is kind of random, right? And then you could also do it with random injections in random places. How often you get the likelihood or SNR squared, which is this big.
So you computed the background from injections. So you injected GR signals where there were no echoes, inject them in noise, and reconstructed the same?
So we injected echoes, basically, because we are looking, it's a search for echoes, right? So, well, let me just actually remember, because it's a while ago. So we look, in this case, we looked, in fact, what happens here is that there was this echo template. So the idea is that these are well separated. There's GR, and then there are echoes. There are tens of seconds, well, not tens of, like 0.3 second or 0.2 second apart. They're very different from. So you say, okay, so we know where you should see these echoes, but if you go much farther away, like, I don't know, 20 seconds after that, there shouldn't be anything. It should be just random. I said, how often do you see this SNR like this? And you just look at various places, like 10 second, 20 second, 30 second, and we did it a lot of times.
Okay. You did it a lot of times in the sense that you did it with real data and real events. So you look
with real data, real events, yeah.
Okay. So so first, I don't know exactly how you can gain statistics by combining O1 events, because there were 2 O1 events, right? Yeah. The first one and the second one. The second one was pretty low mass.
But we have what wasn't an event, there was LVT, right? So that was,
okay.
Yeah.
So you used, okay, so that's, okay, it's kind of low significance. Okay, yeah. But for example, we don't even observe the ring down of that one, right? So, okay. But anyhow, so what I'm saying is that what I think it would be interesting to do, what I would do, is that I would inject GR signals, so no echoes, in random times in noise, and see how often this comes out just because there's noise with GR signal. We agree on this, right?
I agree. No, okay. So this was the first thing. Indeed. To people, we have done others, and others have done. So let me show you what came next, right? But you're absolutely right. So let me actually go to the next. So indeed, so others try to do the same thing. Just give me, right. So this is the group that used to be at actually, where were they? Hanover, right, Hanover. So they did the same thing that we did. We got p-value of 1%, they got p-value of 2%. And I mean, yes, individual events don't give you significant p-values, but then if you combine them, you get p-value of, well, of order of percent. It's not a detection, but it was interesting. But then it was weird thing that not everything, like the fourth event and third event and fourth event, they don't show it, but first and second event showed it. But anyway, so this is a very marginal signal, so you shouldn't really make too much of it. Interestingly, this group who did had a completely different, it's a part of LIGO collaboration, they had a completely different methods. They found the same thing, this 0.2 second and 0.1 second from these 2 events, which were exactly the same thing that we predicted from Planckian echoes, and we saw, although, I mean, our detection was not very significant, but these were the predictions, 0.1 and 0.2 seconds, and that came from this group 3 years later. And in fact, if you try to so this is from that paper from Salemi et al. So this is the echo that they found in this CWB method. And it seems to be localized at the same, if you try to localize it with the main event, they also appear to be coming from the same place in the sky. So, yeah, no, they don't exactly, so let me.
So the green is what?
Right, so the green is, I think the green is echo, the red is the main event. So we have a base factor for this actually, which is as 5 or depending.
That's a Bayes factor, not a log Bayes factor.
So this is actual base factor, right?
So that's nothing, right? So I can get.
It's not a point of detection. It says that they're consistent with being at the same place, right? So if they were very far, if it was a very tiny number, that would say that they're from different places. So these are consistent. Well, they are close enough to be consistent. I prefer that they're co-located. This is a number that you don't find for co-location. At least we haven't found in any LIGO paper. Anyway, so this is a technical point. But the p-value for these guys, I mean, they have it in their papers. So this is, where is the p-value? It's 0.4% and 3%. So it's not big, but it's an independent method. So
I just, a comment on that. So these are, for people who don't know CWB, CWB is an unmodeled recognition pipeline. So what they're trying to do is that they search for coherent power across detectors. They don't care where it comes from.
That's right.
But that's, so there are some technicalities behind this due with the filterings they do. And so since they use they use, okay, there's several technical steps, but the point is that you reconstruct a template, you can have this ringing just by the filters. So I did that with bias wave, which is kind of a similar thing, using GR injection. So I was creating a GR template with no noise, and you can get this jiggling. So I'm just saying that this result is more difficult to, I think your result is easier to interpret than this because there are some technicalities behind this.
Well, I mean, these p-values, presumably it takes that into account because they do random injections for, these are actual random GR injections. Okay, so I mean, I'm running out of time, so let me just show you, I'm just trying to show you what, okay, so I'm gonna show you two results. So now, the question is, now that we know better, these I give you all the song and dance for Boltzmann echoes and quantum black holes. So can we actually use that to search the data? So that's what we did basically a couple months ago. And again, it's not a huge significant detection. We get a p-value of 0.5%. Now, this is for this particular event, and this event we think is more promising because it's the biggest event. So you get the most ring down that you can get from any LIGO event. Although I'm not actually 100% sure that's correct, but it is the biggest event, the most massive event that LIGO has ever reported. So, so basically the prediction is there's a time for echoes and there's a frequency for echoes that I told you. The time comes from entropy, the frequency comes from horizon frequency. And then we go and look, and then we find basically these repeating patterns. This is in a spectrum. This is for CWB. The CWB, we just see the first one. The second one is not loud enough to be seen. And then we also do what's known as PyCBC, which is just a Monte Carlo Markov chain template-based search. And that also gives you a basically waveform, which is these red guys. So red guys and blue guys are reconstructed waveforms from different methods. So there's a base factor of 7, which is not very big. It's not, you want like 10 or 100 to call it a detection, or 100 probably, and a p-value of 0.5%. So there is something there. So we were the first to look for it in this range, but it's not a detection. And in fact—
Which GR template are you using? What's the baseline GR template?
The base factor for the GR template.
The GR template, what waveform model is that?
It's one that's, sorry, I don't have it here, but the name doesn't, I don't recall the name, but it's in the paper. It's written in the cap, but the name escapes me right now. But yes, it's one of the, that was a big thing that, yes, there was one that Jahed tells me was the best one now, but I don't remember, X-Phenom something. Sorry, I don't remember the name. But yes, there are many different GR templates, and that's actually a big problem that different people, depending on different templates, you get different results. So let me just tell you the last thing before I wrap up. It turns out that if you look at combine all the events, there doesn't seem to be evidence, even though like that event does. So this is actually preliminary. But we try to combine all the events, which is not an easy work, but Jahed has been trying to do that, but running lots of big Monte Carlo chains. And it seems that there is no significant evidence, so this is probability density as a function of the amplitude, assuming that all the events, like 66 of them that we could do it for, have the same amplitude. And basically what he finds is that if there is one, it should be less than 0.5. So what Boltzmann echoes are of order 1. So so it seems that it's not some the evidence. If you say all the LIGO events have the same Boltzmann echoes, it's at least either this calculation is not correct, or we haven't done it quite right, or just not all of them have it. But some of them, for some reason, do, like the 1905. Like the biggest event that LIGO has seen. So this is just going to take a minute. So like this is the posterior you get just for GW 1905-21. But if you try to combine all the events, you just get numbers less than 0.5. which are not entirely inconsistent with each other, but it's just that somehow it's not clear. The situation is not settled, and if you look at the LIGO papers, they have a different way of searching for, they don't really include this event.
Sorry,
Yes,
stupid question. Why should the amplitudes be the same? So they will depend on the system parameters, right? So
that's an exactly, yeah. I mean, the simplest idea would be the amplitude would be the same, but really, yeah, it could depend on the system parameters. Now, the amplitude of echoes, I didn't mean that in absolute sense they're the same, but in the sense that I define them, right? That there's a reflectivity of e to the minus h bar over. But there is an inherent uncertainty with echoes because we don't have nonlinear simulations for this. So there are order one uncertainties from that, and that order one uncertainty could vary from.
But do you scale for the mass? Do you scale for the mass?
Yeah, we have already. Yeah, the mass scaling is there. The real uncertainty is in nonlinear effects, basically how they play in, right? Okay. So I just wanted to say the LIGO has also their own search using base wave, and they do it individual events, and then they don't find it for basically most events or any evidence for most events. So that's kind of the story. That it's a complicated story, but essentially some events show some hints. Most events don't, at least with our current methods, and that's where things are. Future is bright. This paper is with my former student who's actually for the first time tried to put these in numerical relativity with the Caltech group. This is from I guess the last chapter of her PhD thesis. So this is not exactly echoes from numerical simulations, but this is as close as anybody has gotten using some sort of a hybrid method combining simulations, these SXS simulations with some echo prescription. And it seems that basically LIGO, you should get lucky to see it. Right now, the SNR is of order, I mean, less than 1 for at least for typical LIGO events, for 1905-21. But with Cosmic Explorer, you could go as much as 10 sigma. So the future is very bright, both from a model building perspective and from observational perspective. And I think this is a sign of things to come. So let me conclude, and sorry for going over time. And I know there are a lot of open issues. Hopefully we can get to them later. But conclusions, so we are still fighting Einstein's demons in his great war, which is between quantum radiation and gravity. So one battleground is quantum nature of black holes. Most people think that echoes is some radical idea, but I would argue, and I think I laid like for half an hour the arguments I have. If you don't think there are echoes, you don't think there's quantum mechanics. So I think there I said it. Quantum mechanics tells you there must be echoes. The details might be different, but that's kind of the quantum mechanics requires that something like that. Stimulated Hawking radiation gives a very concrete model for echoes. There is tantalizing controversial hints, but I think the jury is still out, and we need more data and better models and methods. Maybe the first measurement of a stimulated Hawking radiation, but I mean, the debate is not settled yet. Thank you.
Just to.
Yes, questions?
Okay, so progress.
Okay, yeah, maybe we can give priority to. Yes, please, Roberto, is it you?
Go ahead. Roberto, do you want to ask questions? I think he just disappeared. Okay.
Okay, so I would like to say, so this is a workshop about the recently found connection between gauge theory, mainly about the recently found connection between gauge theory and gravity. So as Alba, for instance, Alba Grassi talked on Monday of what she found for the connection, about the connection of quasi-normal modes to gauge theory, quantization condition, in particular, Nekrasov partition function of n equal to gauge theory. Other people in CISA, Bonelli, Tanzinian students here, Jossa and Panellitic, found still another connection, not for quasi-normal modes, but for the so-called gray body factor or absorption coefficient, which, as I understand, quantifies the Hawking radiation emitted by the black holes. So they computed this through this connection of gauge theory, through the Nekrasov partition function. Yes, we also, me, Gregorio, and my supervisor, Fioravanti, think we can connect both. Very good. To integrability. Yes, we have written an article on quasi-normal modes. We added a comment on the gray body factor, even if we have not given the details on this. So I wanted to understand. So is this gray body factor absorption coefficient, which is basically, let me see. So yes, it's what the factor which corrects the black body spectrum makes a gray body factor. Yes, is related to what can be related to what you said of Hawking radiation. So, as I understood, the stimulated Hawking radiation you find in not actually as Hawking radiation, strictly speaking, but in the gravitational wave signal. So,
I mean, these are all related to each other. So these are all in this picture, okay? So in a standard picture, quasi-normal modes are up here. So those are given by the angular momentum barrier. So those are modes that kind of decay exponentially. Sorry, the time they decay exponentially, I guess with the space, actually they blow up. But they are ingoing in the horizon and not going at infinity. What happens if you put this quantum fuzz here? Then you get a different set of quasi-normal modes. It turns out actually these quasi-normal modes disappear when you do that. But you get a different set of quasi-normal modes which are stuck in between these guys, and they last much longer. Now, the gray body factor has to do with the transmission through this angular momentum barrier. And then the reflectivity that I told you at the horizon, the Boltzmann reflectivity sits here. And the interplay of those, basically, the product of gray body factor and then reflectivity at the horizon, when that becomes one, that gives you the new quasi-normal modes, basically. So they're all kind of tied together. And you need to know all of them to kind of get the new picture.
So, so my question was in particular, so can you also measure the gray body factor, observe in some way, calculate from observations, this gray body factor, from that the signal you are showing?
The gray body, yes, the gray body factor is just from this guy, if that's what you mean. Yeah. It can be? Right. Yeah.
Okay.
Yep, I agree.
Okay, thanks.
Thank you.
So if I can, before we break, a very quick question about the 66 event that you mentioned in the end. So maybe a question to you, maybe to Gregorio. So by considering events in which we don't see the ring down, aren't you sort of over-penalizing the test? Or
sorry, but are you saying, oh, right. No, so...
Because for many of those events, you don't
right.
expect to see anything,
so
right?
That's why we try to do the proper calculus. So for those, then you get very large, you don't get very good constraint on echoes, because, so the idea is that, is there a universal parameter which is the same for all the black holes? And it's not just the raw amplitude, because the black holes are different, they have different masses, different SNRs, and so, but given that we estimate the parameters from GR, so there is essentially the same way that you fit a model for GR, there are mass, spins, things like that. Then you add an additional set of parameters, which is the additional set of parameters with the position where you put the walls, and like the phase of the echoes if there's a phase shift, and then 1 is this basically this relative amplitude. So effectively it's just amplitude of the echo to the main signal. If you want.
No, I was not talking about I was talking about the work in progress 2 slides before.
Yeah, no, I know what you're talking about. Yeah, right. But it's not that amplitude is not is a normalized amplitude. It's not the one.
Essentially, what I'm saying is because you are looking, you are using events where we don't expect to see them.
Right. So those,
isn't that somehow like giving you a smaller number than it should be?
Yeah, but if you do it in the proper Bayesian way, then it wouldn't, right? Because those ones, they would be just flats here, but the ones that have good constants, they would be falling rapidly or rising. So that's the proper Bayesian way of doing that, right? But that's assuming that they all have the same, proper amplitude, right? And then, but if there are parameters, for example, the mass ratio of the binary, that's the obvious one, or spins. If they control this thing, then all bets are off. We don't know. Yes.
So I completely agree with you. So if you do it in the Bayesian way, it should be okay. It's like doing Hubble constant from all the events we have. We don't use only the loud ones, right? We use all of them, so it's okay. And so you're right in the sense that you should be careful in using low significance events, because in that case, you could have, if noise is comparable to the signal, you could get spur peaks just because of noise. But for example, in the testing GR catalog, we have, so in LIGO and Virgo, we claim detection with when the events are of a certain significance, but we test GR only with higher significance, right? So that it cuts in half the number of events. So if you use only the significant ones, I think what they're doing is okay. But so you're saying you're multiplying them because you expect them to be different?
Well, I mean, these are of course different events. So the statistics is independent, but then if they are all measuring the same amplitude, then you multiply the probability.
No, I agree. The likelihood, yes.
Yeah.
But you could do also something else, which is called hierarchical analysis. So in the idea is that you have an underlying population, you have an underlying distribution, right, which will give you different amplitudes for different signals. But there is a population of black holes, right?
Yeah.
So there should be a distribution of the amplitude, even if they are different, right? But there will be, some amplitudes will be more probable and some will be less probable. So you have a parent generating distributions, which will give you the observed one.
Right.
And you can reconstruct that. So you don't care if they are different. You can just reconstruct this parent distribution, and you can say, so if in GR this should be 0, so it's a delta function with some, okay, it's not a delta function because there's errors, but you can reconstruct this, and it's actually quite, we already do it, so maybe we can talk about this.
Absolutely. No, I think that's great. That's the place to go, indeed. Yeah. Very good. Okay.
Okay, so I think we should cut here for a coffee break, and there will be a discussion session. So if you have other questions, we can ask. And yes, so let's thank him again.
Thank you.
So now.